the Pioneer Voyager anomalies. While the outer belt argued in graphs, a different kind of whisper came from hardware built in the 1970s. Pioneer 10 and 11, little spinning buses with dish antennas, slipped past Jupiter and Saturn and kept going. Navigators at JPL listened by timing radio pings that left Earth, hit the spacecraft, and came back, a two-way Doppler heartbeat. The stakes were simple and brutal. If the numbers drifted, either our physics or our mass map was wrong. At interplanetary scale, a millimeter per second of error matters. Here's what the team saw. After they were far from the big planets, the Pioneers picked up a tiny, steady sunward acceleration, about 8 times 10 to the minus 10 meters per second squared. That's a gnat leaning on an elephant, but it was relentless. The tracking folks tried to kill it every way they knew how. Solar radiation pressure, too small that far out. Gas leaks. The spin-stabilized design didn't favor a one-way push. Software bugs, multiple independent codes agreed. In the back room, someone muttered, "Something S out there," and someone else replied, "Or something S in here." Action moved into the weeds. Every watt of heat on those spacecraft had a vector. Radioisotope generators ran hot, their warmth soaked into struts, boxes, louvers. If the heat radiated unevenly, it would push the craft, a photon rocket you never meant to build. Engineers dug up ancient blueprints and thermal vacuum logs. They modeled fins, paint aging, even the way dust might have dulled surfaces. The thermal recoil hypothesis grew teeth. When they ran the improved model against the Doppler residuals, most of the anomaly vanished into the heat, consistent with later detailed analyses that attributed the effect primarily to anisotropic thermal radiation. But here's the catch. Most is all. Even in best-fit models, some sliver of unexplained drift clung to the data, especially late in the missions when the power was lower and the geometry simpler. Was it just the last 5% of a messy thermal map, or did a residual hint at something external? The community's consensus leans thermal, but precision here is brutal. A calibration typo can masquerade as new physics, and these were one-off machines with aging quirks. Meanwhile, the Voyager's different beasts entirely were 3-axis stabilized, with heaters flicking on and off, antennas slewing and gravity assists yanking them into the deep. Their trajectories needed periodic corrections, and the tracking was noisier. Still, navigators noticed oddities. Tiny biases in Earth-based Doppler versus on-board counters, coarse tweaks that felt slightly off compared to fuel budgets, deep space tracking jitter that seemed to have a seasonal flavor, ionosphere, troposphere, station thermal flex, all suspects, pattern or noise. Most days, noise won. But in the hallways, the Pioneer story kept people cautious. If a part per billion force could slip through, what else might we be normalizing away? What nobody knew then was how the outer architecture would soon look sculpted. The idea that faraway mass might exist wasn't born from the probes, but the probes trained the culture to respect small, steady discrepancies. A discipline measures itself by what it refuses to shrug off. The Pioneer Anomaly, thermal at heart but instructive, set a standard. Prove it in the hardware before you rewrite the sky, or the other way around. Fork the road, artifact or mass. If thermal recoil and modeling imperfections explain everything, the lesson is humble. Deep space navigation is a master class in bookkeeping, and small forces add up. If any residual remains, the cleanest external culprits are gravity and drag. Drag from what? There's no ether out there, and interplanetary dust at those distances is far too thin to matter. Gravity from what? A distant, massive object wouldn't pull sunward on both Pioneers the same way unless its reach dominated the neighborhood. That raised eyebrows. A planet-sized body at a few hundred AU could leave fingerprints, but a brown dwarf or super Jupiter much farther out would act more like a slow, broad wobble on the solar system's barycenter rather than a neat, sunward tug. Action pivoted to cross-checking. Could ephemerides, our best fits to planetary positions over decades, absorb or reveal a hidden pull? Teams compared radar ranging to planets, spacecraft flyby data, and occultation timing. Any unseen mass adds a subtle bias to how the solar system dances around its center of mass. The more precisely you pin Mars, Jupiter, Saturn, and the outer moons, the less room you leave for ghosts. Constraints tighten. The parameter space for an external heavyweight shrank, not to zero, but to a narrow alley. Far, cold, dim, and lazy in the sky. Then came the discipline's quiet confession. Even if you nail the physics, the instruments carry their own weather. Earth's rotation jitters timekeeping. The deep space network's dishes breathe with sunlight and cool with night. The plasma between planets hisses on the carrier wave. Navigators live in that fog. One veteran said, "You learn to separate the static you expect from the signal you don't, and you never fall in love with either." Impact immediate. The Pioneer case didn't prove a companion, but it inoculated the field against easy answers. It showed how an unmodeled push can fake gravity and how gravity can hide behind a push. Long term, if a distant mass exists, its cleanest signatures wouldn't be a tidy sunward acceleration. They'd be timing scars spread across many systems, planet ephemeris offsets, comet delivery statistics, and the slow procession of distant minor bodies. The probes were the first nudge, a reminder to look for coherence across datasets, not drama in one. Here's a micro-story from the console. A navigator in Pasadena watches a Doppler residual drift a hair redder than expected. He rechecks the tropospheric model, swaps in a fresh antenna calibration, and the line snaps back almost. He leaves a note. Residual persists at 0.2 ms. 10 years later, that scrap shows up in a meta-analysis. It doesn't solve Nemesis. It earns the next question. And that's the pivot. If something big is out there, it shouldn't only tease the radios. It should leave marks in deep time on rocks and bones. If gravity writes, Earth keeps the receipts. We turn from dishes and Doppler to a colder ledger, the rhythm of extinction itself. The extinction rhythm, 26 million year signal. Open the rock ledger and it reads like a heartbeat. In the early 1980s, two paleontologists, David Raup and Jack Sepkoski, weren't hunting planets. They were counting funerals, compiling the most complete database of marine life extinctions anyone had attempted. Family by family, epoch by epoch, they marked when diversity plunged. Then they ran the numbers and a pattern surfaced that made geologists sit up. Sharp upticks in extinction, spaced about 26 million years apart, as reported in 1984. Not perfectly metronomic, this is Earth, but regular enough that chance started to sweat. Stakes land fast here. If life's worst days arrive on a schedule, something outside the usual volcanoes and tectonics playbook is tapping the glass. And if that schedule lines up with a long, cold orbit, we are not just passengers, we're on a route. Hook for the skeptics. If this signal fades under better dating, the whole Nemesis idea collapses. If it survives, the sky owes us an explanation. The fossil bed from our opening scene stops being a tragedy in one place and becomes one tick on a cosmic clock. Action moved from spreadsheets to mechanisms. What could swing at Earth with a 26 million year arm? The Oort Cloud, that distant sphere of icy bodies, is a loaded dice cup. Disturb it and comets rain inward. You don't need a Death Star. You need a slow, periodic perturbation that shakes the outermost orbits just enough, then steps away. Comets that survive the long fall turn into long-period visitors. A few are on collision courses. The Alvarez team's iridium layer at the dinosaur boundary had already told everyone that rocks from space can end eras. If those rocks arrive in waves, the culprit might be orbital, not random. That's where the Nemesis idea took shape. Hypothesis, not proclamation. A dim companion to the sun, maybe a red dwarf or brown dwarf, on a wide, eccentric path taking tens of millions of years to loop around. At periapsis, it passes close enough to tug the Oort Cloud's outer shells, sending a fraction of bodies inward. Earth, sitting far downstream, feels the hail. Then Nemesis recedes, the influx wanes, and the biosphere rebuilds until the next pass. Get this, people actually mapped the proposed timing of those passes against Raup and Sepkoski's cycles. It wasn't clean enough to declare victory, but it was aligned enough to pour serious attention into the sky. The companion didn't need to be bright. A brown dwarf could be almost invisible in optical light. Infrared would be the way to catch it, or gravitational breadcrumbs. But pushback arrived with scalpels, not slogans. Dating the fossil record isn't a wristwatch. Error bars stretch and compress. Some peaks moved when new strata were calibrated. Volcanoes don't care about stars, and flood basalts like the Deccan Traps can wreck climate on their own timeline. Sea level changes, ocean anoxia, plate reorganizations, each can thin life's ranks without help from the Oort Cloud. More, later analyses suggested longer cycles, around 30 to 32 million years, or multiple overlapping periodicities superimposed on a messy background. The signal was there, but its exact beat seemed to drift. And that's actually a point for orbital triggers, not against them. A bound companion in the sun's far suburbs would feel the galaxy's tides and passing stars. Its orbital period would not be a granite number. It would wander by 10, maybe 30% over hundreds of millions of years. A 26 million year average could show up as a band, not a razor line. If someone insists on perfect periodicity, they're asking the wrong sky. Meanwhile, geology brought in independent clocks. Some cores showed spikes in extraterrestrial helium-3, cosmic dust fingerprints that appeared in clusters. Impact craters on Earth are lousy timekeepers because erosion erases them. But when you stack the dates we still have, you see hints of bunching beyond random. Microtectites and soot layers point to episodes of elevated skyfall. None of these datasets alone proves a marching companion. Together, they whisper, check the cadence. Impact on the field. The Nemesis proposal didn't win a trophy, it won a to-do list. Build better time series for extinction intensity, sharpen crater dating, separate background comet trickle from shower pulses, and crucially, search the sky where a slow, cold object could hide. The controversy hardened the science. Every counterexample forced cleaner methods. Every persistent pattern bought the hypothesis one more season. Human moment. A paleontologist in a desert trench flips to a fresh page and writes, another abrupt boundary, same signature minerals, different basin. He's not thinking about brown dwarfs. He's thinking about whether the sea retreated too fast, whether the ash line came from a nearby arc. That night, someone emails him a preprint plotting his new date on a 30 million year cycle curve. He replies, could be, or could be local. Both are true until they are. There's a fork that matters. If terrestrial triggers dominate, basalts, anoxia, supercontinent breakups, the rhythm is coincidence layered over a chaotic planet. If an external trigger plays a regular supporting role, then Earth's worst days have an upstream cause that's predictable enough to watch for. Neither path excuses us from the grind of data. Both send us back to the Oort Cloud, because that's the only reservoir big enough to connect a faint, far perturber to mass death here. So does the pattern survive scrutiny? Enough of it does to justify a renewed search. Not a proclamation, not a press conference, just the next round of hard constraints. If a companion exists, its orbit must be wide, its light faint, and its influence seen more in timing and geometry than in photographs. Infrared eyes have something to say about that, and their silence is the infrared ghost clue. If a companion hides in the dark, infrared is where you corner it. That was the bet. Brown dwarfs don't shine like stars. They glow with leftover heat, cool embers in a cold room. So we built eyes for heat. The 2-micron all-sky survey, 2MASS, swept the heavens. Then WISE, the Wide-Field Infrared Survey Explorer, mapped the sky in 4 infrared bands with a sensitivity leap that should have snagged many warm neighbors out to several light years. Stakes couldn't be clearer. If Nemesis glowed, WISE would have had a fair shot. Here's the catch. Brown dwarfs cool with age. A young one might be toasty enough to pop in near-infrared. An old one sinks to a few hundred Kelvin, radiating mostly in the mid-infrared, dimming hard with distance. And luminosity falls off as the square of distance, so every extra AU is a tax on detectability. WISE did pull in a trove. Why dwarfs so cold some were not much warmer than room temperature, and a near-complete census of warmer brown dwarfs within a few parsecs. The result many took as a verdict: no obvious nemesis in the backyard. But verdicts need footnotes. WISE's completeness tails off for the coldest, faintest objects, especially if they move slowly enough that they don't betray themselves with big proper motions between survey passes. A companion on a multi-100,000-year orbit would crawl against the stars. If its temperature sat at the low end, say a wide dwarf colder than expected, or if it sat well beyond 1,000 AU, its flux could slide under the noise floor. Add in confusion. Near the galactic plane, the sky is crowded with infrared sources. Distinguishing a faint, slowly drifting ember from a distant galaxy or a mottled patch of cirrus is not trivial. Action moved to constraints. Astronomers used WISE and two masks together to search for high proper motion cold objects. They found many, and in doing so they boxed the parameter space hard. Within tens of thousands of AU, anything the mass of a typical brown dwarf, warmer than a few hundred Kelvin, and not hiding right in the glare and confusion zones, should have shown up. That shrank Nemesis from any dim star to extremely cold, likely very distant and maybe lower mass than a star, a super Jupiter or a borderline brown dwarf. Non-detection wasn't a kill shot, it was a corral. Meanwhile, instrument people whispered about floors and ghosts. Infrared detectors carry quirks, latents from bright sources, band-to-band color terms that can misclassify a weird spectrum, and calibration drifts that live at the edge of faintness. Teams combed the catalogs for outliers with odd colors that didn't fit standard templates. Some were artifacts, some were galaxies, a few were real ultra-cool dwarfs. None screamed solar companion. Loopholes stayed on the table. Put the object on a high-inclination orbit well out of the ecliptic, and the all-sky coverage is still there. But follow-up can lag because most survey pipelines and ground campaigns concentrate near the ecliptic where most moving objects live. Push the period long, the motion slow, the temperature low, and a real thing can look like a barely moving speck whose color mimics a distant galaxy's dust glow. And the further you shove it, 50,000 AU, a quarter of the way to the Oort Cloud's edge, the fewer photons you get, no matter what. Human moment. In a small office, an astronomer clicks through WISE codes, eyes aching at the grain. There's a source that's just above the threshold in W3 but barely there in W2, nothing in W1. Over 5 months, it shifts by a fraction of an arcsecond. She flags it, writes possible cold HPM, and sends it to a colleague. The reply a day later: galaxy, extended in deeper stack. She sighs, opens the next tile, and keeps hunting. Meanwhile, other constraints piled in. If a massive body lurked at a few thousand AU, its gravity would tug planet ephemerides measurably. We don't see that. If it were a normal M dwarf within a light year, even dim, it would have been catalogued ages ago. WISE's null means a traditional, bright nemesis is off the board, but the universe is generous with gray areas. A low-luminosity companion, massing more like a super Jupiter or a cold brown dwarf, tucked beyond a few thousand AU, remains a mathematical resident in the model's spare room. Therefore, non-detection narrows properties. It doesn't kill the idea outright. It tells us any companion must be faint, cold, distant, and slow. It points to where to look smarter, not louder, stacking epochs to tease motion, cross-matching colors to isolate non-galactic spectra, and leaning on astrometry to catch reflex wobbles instead of light. Infrared didn't slam the door. It made the hallway narrower. Impact ripples through the narrative. Infrared silence shifted the search from spot the ember to prove the pull. If light won't volunteer, geometry has to testify. That loops us back to the outer solar system's architecture because there's another clue baked into the orbits themselves. The Kuiper Belt isn't just clustered, it's tilted, warped in a way that suggests a long, patient torque from something inclined. If the sky won't show us a face, maybe the disk can show us a handprint.